but I'm excited to talk to you today about one of my favorite topics, actually, which is the evolution of stellar rotation. And today I'm going to be focusing on kind of not just the evolution of single stars, not just the evolution of the outside rotation rate that we can measure, but also the interiors of stars and the impacts of stellar companions, either planets or other stars. And the reason I love talking about rotation so much is that rotation is both important and useful. It's important because rotation is one of the few actual properties of a star. When you model a star, you start out with a mass of that star, say 1 solar mass. So rotation is one of the few core properties of a star. When you model a star, you give it a mass, 1 solar mass, you give it a composition, maybe solar composition, and maybe you give it an initial rotation period. But from that point, pretty much everything else is physics. You know something about the physics of nuclear reactions, about convection, about opacities, and all of that tells you how that star is going to evolve and change over time. The other important thing about rotation is it's actually one of the largest uncertainties in stellar physics. It interacts with things like convection, it interacts with things like magnetism, it impacts the properties of the star in a lot of different and challenging ways. But rotation can be very useful. It correlates with things like age or magnetic properties that are very hard to measure directly about a star, and so you can use it to infer something about how that star is changing over time. You can also often use rotation as a tag of interactions. If you have a tidal interaction, that'll affect the rotation of the star, and so that will tell you something about its history. So in this talk, I'm going to try and convince you that we have empirical data now, detailed empirical data on the evolution of stellar rotation, and that binaries are not a negligible part of that. That something like 10% of stars or more interact with something over the course of their lifetimes. And finally, that I'm going to try and convince you that rotation is impacted by a whole bunch of different important physical processes, things like angular momentum loss, things like that loss turning on and off over the course of the star's life, the internal angular momentum transport between the core of the interior of the star and its surface, as well as the effects of tides and tidal synchronization. So in this talk, I'm going to talk to you about stellar rotation measured a couple of different ways. One that you might be familiar with is looking at the stellar rotation velocities from a spectrum of the star. So you see the star has lines. If the star is rotating, some parts of those lines are blue shifted or red shifted, and so that broadens the line. And the amount of that broadening can tell you the rotation velocity of the star modulo the inclination angle that you're looking at it. Another way you might be familiar with measuring rotation periods is to look at spots as they come into and out of view in front of the star. We'll modulate the brightness of that star with some period that's related to the rotation period of the star. The third way we think about stellar rotation is through astroseismology. So if you look at either the spectrum or the light curve of a star over time, you can take the Fourier transform of that, and it picks out a lot of different processes that are happening at the star. At low frequencies, and this is a Fourier transform of our sun, at low frequencies, you see the effects of spot modulation and rotation. At medium frequencies, you see the effects of granulation on the surface of the sun, and at high frequencies, you can see things like the stellar oscillations. It turns out that that's not just true for our sun. If you monitor other stars with this sort of precise high cadence monitoring that we get for something like Kepler or TESS, you also get a light curve of the star. That light curve has variability, which is intrinsic. It's not noise, it's signal. And so when you take the Fourier transform of a light curve from Kepler or TESS, you see this same sort of pattern, where at high frequencies, you see the effects of instrumental noise. At lower frequencies, you see the effects of convection, and kind of in the middle, you see this characteristic peak of oscillation modes. If you zoom in on that peak of oscillation modes, it's got some sort of Gaussian envelope with some characteristic frequency that's related to the surface gravity of the star that you're looking at. If you kind of squint at this, you see there's kind of a regular pattern in this picket fence of characteristic spacings that happen to scale as the mean density of the star. And that means that you have something that scales with m over r cubed, something that scales with m over r squared. You get an independent mass and radius for the star, which is very convenient if you then want to characterize it. However, you can go farther than that. If you look at those individual oscillation modes, they have characteristic frequencies and patterns that pick out particular oscillation frequencies and type of frequencies. So here I've shown you the kind of the radial oscillations, the dipole oscillations, and the quadrupole oscillation. And they are they're spaced by this characteristic frequency. So if you kind of stack the spectrum on top of each other, you get these ridges that show you something about the detailed structure of the star. And if you look at some of those modes, those L=1 modes that are offset from that kind of standard ridge, you might see this splitting that looks like you don't have just one mode, but you have two. And that splitting is telling you, like a Doppler splitting or a Zeeman splitting, about the rotation rate of the region of the star where this oscillation mode is spending its time. And so you can use that to infer the rotation of that star. In this talk, I'm going to talk about differential rotation between the interior of the star and its surface. I am not going to talk about the latitudinal differential rotation, partly because it's very hard to constrain. On our own star, we know that the equator rotates faster than the poles, but doing that for other stars is extremely challenging. And people have tried to do models. Can you measure it just from the photometry? It's really hard. Can you do it from the astroseismology? Well, maybe for a handful of stars, but it's hard to do. And so we don't really have a great sense of what the latitudinal differential rotation pattern looks like on other stars. Okay, but now we can actually get into the evolution of those stars. So you start out with a cloud of gas that's collapsing down into a star. In that process, it forms a circumstellar or protoplanetary disk, which now we can image in beautiful images from things like ALMA. And that disk is a way of regulating the angular momentum content of the star as it contracts. It would spin up to break up, but it can dump angular momentum into the disk. If you look in young clusters, you see that stars with disks tend to spin more slowly than stars without disks. And in this talk, I've used a lot of different axes for rotation, periods, velocities, all of these things. Sometimes they're up, sometimes they're down. So I've tried to put a little fast label on the fast side in all of the plots, hopefully. The stars without disks tend to spin faster because they're not regulating their angular momentum with the disk in the same way. Those disks have a characteristic lifetime, something like 3 or 10 million years. They start to dissipate in young clusters. And so that means that they kind of leave in this initial distribution of rotation rates, which is probably related to when each star's individual disk evolved, dissipated, and decoupled. But you can go out and measure with beautiful photometry what that distribution of initial rotation periods is, how it depends on the mass of the star, and what the range is. You can then look at a slightly older cluster and see how the distribution of rotation periods in that cluster has changed over time. And you'll notice in like the first few million years, as the stars are contracting, as the disks are dissipating, that contraction, if you conserve angular momentum, will spin up the rotation of the star. And so they tend to contract, spin up, spin faster, so move downwards on this plot. As you get to older ages, the disks are gone, so they're no longer an important part of setting how the rotation evolves, but you can see that the rotation seems to slow down over time. And we think that's due to the effects of stellar winds. So you're losing mass in a wind, that wind is magnetized, so the particles are carrying away more angular momentum, and so the star should slow down over time. You can see that that's a mass-dependent process. You can see that there's clearly a bunch of physical patterns imprinted here, but you can clearly track what's happening. Now, when you think about the winds and the stellar winds in the sun, right, it's a complex feature, right? It's time-dependent. It depends on the magnetic cycle of the sun, depends on the amount of particles and mass that's lost and their velocities and their magnetic field structures. In other stars, we don't have any of that. So we tend to simplify quite a bit. So the original simplification that people made was they measured rotation rates of solar-like stars in a couple of clusters on the sun. They noticed a polynomial relationship where the stars slowed down over time, And so we fit a relatively simple function to how the rotation periods would evolve. In more recent years, we've realized that the rotation and magnetic fields and winds should be a little bit more complicated than that. And so people who are doing 3D hydrodynamic, magnetohydrodynamic simulations are arguing that the evolution in the wind loss should be related to things like the rotation rate of the star, the Alfvén radius, the magnetic loss, the mass loss rate, the convective overturn timescale, the magnetic geometry, all of these things, which they parameterize by things like scalings with the luminosity of the star, scalings with things like the radius of the star, the photospheric pressure, and the convective overturn timescale. And so it's kind of the middle of the talk, I'm going to come back to this argument that we really need these more sophisticated angular momentum loss laws in certain regimes. But in general, they preserve the same formalism where stars slow down over time. And that slowing down over time is not something you have to take on faith anymore. You don't have to believe the theory of connecting these dots, because people have gone out and measured in various open clusters at various ages what the evolution of the rotation periods are. And in stars like our own sun, you see this sequence where as you get to older and older clusters, the stars are slowing down over time. That's this loss in the wind. You can just track it. Now, in some of the lower mass stars, you'll notice that this spin down over time seems to kind of slow for a while and then spin up and then increase again, so they slow down more. We think that's probably related to how the interior and the exterior of the star are communicating. So you can make models of how the angular momentum of these stars at a particular temperature should slow down over time. If you have the whole star basically act as one single solid body, it spins up fast and then it slows down. If you have the inside and the outside being separate, then you spin up the outside, but not as much because you can't spin up the core. And then you kind of just lose angular momentum from the wind, so it slows down much faster. Neither of those, and that's the solid and the dashed lines, are quite consistent with what we see. So there's probably some intermediate case where, angular momentum from the interior eventually gets transported into the envelope and lost in the wind. But that happens over some time period. And you can do some modeling and say that the time period over which the core and the envelope couple is probably mass dependent. That makes sense. The cores will be different sizes, the shears will be different. But you can model this. And the nice thing is, if you're interested in mixing, which should be related to rotation in some of these regimes, these models that couple the core and the envelope over time actually give you a better match to some of the mixing diagnostic signatures like lithium in young clusters. So hopefully I've convinced you that on the pre-main sequence, stars have strong mass trends in their rotation rate. We don't actually have a lot of information on the metallicity trends because most of the stars in the solar neighborhood are sort of solar metallicity. But we've noticed in a couple of cases that binaries often rotate more rapidly than single stars, and that evolution suggests that there should be strong radial differential rotation in these stars with a mass-dependent coupling time. Normally over Zoom, I pause here for like 30 seconds to see if there are any clarifying questions or if I have dropped my internet connection. So I think I'll keep that. I'll pause for 30 seconds and see if there are any clarifying questions before I go on. Go ahead.
So regarding the metallicity trends, are the populations, for example, in the Magellanic Clouds too far away to do these kind of studies?
Yeah, so the things like the Magellanic Clouds or even like the outer or inner parts of our own galaxies, it's really hard to find kind of young stars that are bright enough to be able to measure the periods or velocities over long time scales. So I haven't seen much of that work done.
I guess I was thinking specifically of the pre-main sequence in 30 Dorados where you have young stars, but then maybe they're swamped by the massive stars, so you can't get the same noise.
Exactly. So you get different information, but I have not seen this sort of work done for low metallicity stars. Yeah, go. I think there's a push to talk.
Okay, good. This might be something that you would prefer to answer later, or that you're going to get to later on.
Yeah.
But I'm wondering about the binaries and whether or not there's a relationship between the rotation rate and the mass differential, or between the two.
Yeah, that is a super fun question. I have not seen any work done on that I'm aware of. You should see, right, there are close binaries where there's tidal interactions, and so that should sort of scale in some predictable way. Wider binaries where the disks are impacted, I don't think we have great of constraints on, and I haven't seen anybody try and use that rotation to diagnose how those disks interacted. But I think that's actually a really cool project idea. Okay, so I'm going to continue on to the main sequence and show you a little bit of work. This is done with Ellis Avalon, who's a graduate student in Hawaii, where we looked at the rotation periods and velocities of stars on the main sequence. When you do this, and I've marked kind of masses for these, you see there's a break in rotation where there's stars that are hotter or more massive tend to rotate rapidly. These are the stars that don't have deep convection zones, don't drive the same sort of magnetized winds, so they don't slow down in the same ways. At lower masses, you see that angular momentum loss over time as stars evolve upwards on this plot. They go from shorter rotation periods in sort of yellow-green to longer rotation periods in kind of blue. So that's sort of the pattern you expect in these low mass stars on the main sequence. And then you can ask, we didn't have a great metallicity range in this sample, but you can look at the metallicity range and see if there's any sort of metallicity dependence in the main sequence rotation rates. And we didn't really see anything. There have been previous works that saw a stronger trend than this. There have been works that have argued there should be a trend. I don't know if it's a difference in sampling. I don't know if it's a combination of temperatures or where we are. But it seems like the metallicity dependence is subdominant, at least in this regime. But whether it exists or not, isn't it still an open question? What we did see a nice trend with was binarity. So we could look at stars that were presumably single, stars that had wide binary companions as indicated by their Gaia renormalized unit weight errors, and those seem to have similar rotation periods to the stars we marked as single. But for stars in close binaries marked by radial velocity variations, you could see that the stars tended to spin faster. So there's probably some tidal interactions, tidal effects going on there. And that's kind of the same picture you get if you look at stars in open clusters. If you pick out the stars in an open cluster that are rapidly rotating, they are often stars that are also have other indicators of binarity. Close companions, they're blue stragglers, things don't match quite right. And so there's probably some relationship between binarity and rotation for some population of stars on the main sequence. But that's the outside of the stars. You might ask, what about the interior? So in the sun, we can do detailed mapping of the interior rotation profile of the sun, where you see that latitudinal differential rotation in the surface convection zone on the right side of this plot. As you go to the radiative interior of the sun, the rotation seems to be relatively constant, relatively simple, down to about the core region, which is hard to probe in helioseismology. There have been some arguments that it might rotate a little bit faster than the rest of the interior, but it's not that much. Unfortunately, in most other stars where we try and do astroseismology, we don't get that same detailed interior picture for main sequence stars. But what we can use is close binary systems to probe the rotation profile in the interior. Because if you think of a binary system synchronizing, right, it should be synchronizing with some average rotation of the star. And if that rotation is held to some strongly radially differentially rotating number or profile, then the rotation period of the orbit should match the rotation period somewhere in the interior of the star, depending on what that profile is, which means that the rotation period at the surface will not be the same exactly as the rotation period, or as the orbital period of the binary. And people have characterized a large number of close binary systems. In general, you find very little difference between the orbital period and the rotation period in such systems. And so that argues that there's relatively minimal radial differential rotation in these solar-like stars, which is kind of consistent with what we're seeing in our own sun. So we argue that on the main sequence, we see strong mass trends, we see subdominant metallicity trends, but that binarity can be important with close binaries generally rotating faster, but the radial rotation profile is relatively simple, and assuming a solid body is not a terrible idea. I'm going to again pause for 30 seconds and check for questions. Go.
I don't know a ton about astrostar modeling, but for the targets that you are looking at, do star spots ever complicated?
Yeah, so people have kind of looked at this a little bit, trying to understand whether rotation and activity impact the astroseismology. So usually the rotation, the peak from the rotation is at a different place than the kind of oscillations characterizing the star. So they don't interfere quite directly. You could argue that there should be some splitting of the modes, but that's really a different problem and kind of separable. They're in close binaries in red giants. You see that as they get close binaries and spotty and active and rapidly rotating, the oscillation amplitudes decrease. That's less obvious on the main sequence. Actually, people are still arguing whether that's the main reason you can't detect oscillations in some stars. And I think the answer is probably no. So it impacts it a little bit, but not in a way that we think biases too much of what we're trying to do with it. Yeah, question.
When you say the binary population is rotating faster, and you just discussed how some of that is attributable to tidal interactions, if you take the subpopulation, not the extremely wide astrometric binaries, but the wider spectroscopic binaries, are they comparable to matched isolated main sequence stars, or is there additionally something about forming as a binary that makes the components rotate faster?
Yeah, so that's a question I would love to see a clean answer to. I haven't seen it, which doesn't mean it doesn't exist. But I haven't seen a clean answer. I think there are some stars like in the open clusters, you can say, well, does it have a binary? Well, yes, but it's wide, so I don't understand why the star is rapidly rotating or very slowly rotating. And so you can pick out individual examples, but I'm not sure I've seen a more like homogeneous study, like as we push the Gaia radii in, as we push the radial velocity radii or orbital radii out, in that kind of middle region, how much it matters. But I think that'd be really interesting. Cool. Okay, so over the course of the main sequence lifetime, with various tracers, you can watch the stars slow down over time. But if you look at this kind of carefully, you'll notice this kind of region of old stars, kind of more than halfway through the main sequence, that are rotating a little bit more rapidly than we expected. Now, the ones that are rotating a little more slowly at the very edge of the plot, well, maybe that's, the radii is starting to increase. So, drawing just a simple line on this plot is probably not sufficient. But it was odd that these were all rapidly rotating. And so people like Ruth tried to do very careful fits of this. Can you come up with a scenario to explain these sort of rapidly rotating old stars on the main sequence? And found it was pretty challenging under kind of the standard assumptions that we were making. And so then people started to use this to argue that there was some transition in the angular momentum loss, something like halfway through the main sequence, where the stars slow down over time for a while and then stop slowing down at some, Rossby number or characteristic balance between rotation and convection. Now, that was kind of a controversial statement. You want to argue that right at the age of the sun, something physical changes about rotation. It's a hard sell. And so people have asked a lot of questions about that. And one of them is about the detectability of long periods, right? As you get to long rotation period, the spots amplitudes get lower, the periods get harder to detect. And if you look at the distribution of stars where you detect a period and stars where you don't detect a period, you really stop detecting spots at about the same time that this transition is happening. And so there were still questions about whether this was a real transition or this was a detection bias. Luckily, people have tried to work this problem in a couple of different ways, trying to figure out if this is a detection bias. So this is very recent work by Trevor David, looking at if you take a distribution of stars, a population, and kind of project them forward in this kind of standard scenario, they should slow down over time. And even if you stop detecting them at some point, there shouldn't be any kind of feature in the distribution. It's just kind of cut off at that point where you stop detecting them. Whereas if you argue for this transition in the braking, then suddenly you've got, twice or 3 times as many stars spinning at kind of the same rotation period. And so you should see this pile up in the distribution of these measured rotation periods. And if you actually look at the distribution of measured rotation periods, you start to see this pile up. The other thing is you can try and measure the rotation a different way. So if you use these astroseismic rotation rates, which don't have the same need for a spot to be there and detectable, you also see this pile up that's much more consistent with this sort of transition in the angular momentum loss. So this pile up of weakened magnetic braking, which is great. So now we have this new theory we have to incorporate in all future models of stellar evolution, that somehow about halfway through the main sequence, stars stop spinning down. And so that means when you kind of project forward in time towards the end of the main sequence, the subgiant branch, and even the red giant branch, right, these stars are holding on to more angular momentum than you would have expected. So in kind of a model that takes into account various masses of stars, you can go out and measure what the distribution of rotation periods is from each of these different methods: velocities, periods, astroseismic splittings, right? And you can get a distribution, or you can get measurements of the rotation periods of stars as a function of their evolutionary coordinate, or surface gravity in this case. And if you try and make these models with just kind of the standard braking, they should have slowed down more. And so you should see more gaps between stars of various masses in a way that I don't think is as consistent with the data as these sort of truncated braking models. And so you can, when you project forward onto the red giant branch, you incorporate this truncated braking, so you can predict what the surface rotation should look like, even in cases where it's very long rotation periods and very hard to measure. And the nice thing about these kind of subgiant and red giant stars is that you can actually also get a probe of the interior rotation directly from the astroseismology. The modes from the core will mix with the modes at the surface, and so you see these splittings of the core dominated nodes, which tell you about the rotation periods of the cores of these stars as a function of stellar mass, as a function of stellar surface gravity. And you will notice that they are not at all consistent with what we think the surfaces are doing. It looks like the cores contract and spin up on kind of the subgiant branch, and then stay at relatively flat or maybe slow down a little bit over the course of the red giant branch. Now, this is the data from Kepler. We had a little bit of a gap between the stars that might host planets, and so were interesting to the planet people, and the red giants where we thought we could make measurements. So, what's happening in between there was still a question, but with tests, we can start to fill in that gap. We have stars on the lower giant branch, we have stars on the subgiant branch, and you see this kind of smooth transition in the rotation rates of the cores of these stars. And on the pre-main sequence, right, we saw connections between the rotation rates of these stars and the rotation in their interior, and the mixing is traced by things like lithium at their surface. When we look in the red giant samples, we don't see those same simple correlations, which means that probably something else is going on with the mixing and the lithium in these stars. But there is not that same sort of simple connection between rotation and mixing on the giant branch. And people have tried to think about like what the physics of this transport between the cores and the envelopes is. Like, how do you get these cores to spin up and then kind of stay at fixed rotation periods? In general, most kind of simple models of what that physics of angular momentum transport between the core and the surface should be don't really work very well. You can try magnetic fields, you can try various waves, and it just, hydrodynamic flows, like nothing quite works right. And you can try and tune it, but so far I haven't seen a tuning that kind of matches all the different regimes and all the different patterns. So it's still, I think, an open question about what's causing the angular momentum transport, what mechanism is doing that transport of angular momentum. Now, when you look at single stars, right, you can trace this sort of evolution over time, but there are also some interesting cases. And one of them is this lower giant star, where we think there might be some evidence for tidal spin up of the surface. So this is a star where you can make a a model of what the rotation period of the rotation profile of the interior should look like. So from the core on the left side of this plot to the surface on the right side of this plot, the core is rotating fast, the envelope is rotating more slowly. This one has the transition point somewhere deep in the interior, like near the hydrogen burning shell. That's arguable, it's hard to measure, but sure, we'll start out with a model that looks like this. And then you can put on the data for this star. It's a star that has an astroseismic measurement of the interior rotation rate, which matches the model pretty well. It's a star that has an astroseismic measurement of the envelope rotation rate, which is a little bit faster than what we're seeing, but this model doesn't have all the truncated braking tuning. It's not exactly tuned to the star. So maybe just like, 0 point the total angular momentum budget a little bit. But what's really interesting is the star also has a rotation velocity that's measurable. And that's the peak point, which is much faster than the rotation rate of the kind of generic envelope. So somehow angular momentum has been pumped into the very surface layers of this lower giant star. And we argue that the most reasonable way to do that is to have it interact with something, either a large planet or another star. We don't see evidence of a stellar mass object right next to it, but you can only place so many limits so far. But this is kind of one case. And there's an ensemble of these stars that are interacting with something as they go up the red giant branch. And that interaction should happen in a binary in some way that's related to the orbital separation. So you have something here on the x-axis here that's tracing the radial velocity variation, so something that's tracing something about the orbital separation, as well as the rotation velocity that we measure in these stars. And if they're spinning up over time, there's kind of this, parallelogram allowed region of rotations you should see for stars that are interacting with something at around their current radius. And the nice thing is in a sample like Apogee, people like Christine Daher can go out and measure the radial velocity variations. We can measure the rotation velocities from the Apogee spectrum. And you get a pattern that matches this tidal synchronization quite well. The stars tend to populate the kind of allowed regime of where primaries should live and where mass ratios of various levels should be. And so we're really starting to identify quite a number of these stars that are interacting with something on the red giant branch, kind of in the initial stages, in the kind of generic stages, and then afterwards. So for subgiants and red giants, I've argued that sort of you have mass-dependent surface rotation rates, but the core rotation rates seem to be mass-independent, which I deeply don't understand. So if you have ideas about that, definitely let me know. We haven't found too many strong metallicity trends, except for some trends between the amount of binaries and the metallicities of the stars. But we do see significant radial differential rotation, and we know that the binaries can spin up the surfaces of these stars. So I'm going to again pause for 30 seconds and check if there are clarifying questions. Yeah.
What does the astroseismology tell us about the rotation velocity of the envelope? Is that mean rotation velocity of the envelope, or it's the very surface of rotation?
Yeah, so that is one of the challenges of trying to get the envelope rotations from astroseismology. The first problem is you have to subtract off the core rotation, which is big. And then the second is you're getting some average over the region where the modes are spending their time, which has to do with the stellar structure. It tends to probe mostly the very outside of the envelope, but with some sort of sinusoidal kernel of probing into the interior. You can try and play games with the differences between individual modes and what region they spend time in, but the more complicated you make that, doing the detailed measurement is hard. So we've got a project to try and do that better than sort of the generic analysis that was done for the paper where we're taking the envelope rotation for. In general, everybody agrees that it's slow, but whether it's where I put that point or a factor of 2 lower, I think depends on who you talk to.
And sorry, so the seismology obtained omega and B sin I. So B sin I was faster than the seismology obtained omega.
Yep.
And that might be originate from that, typically it's like kernels or something.
So I think it's very hard to do that because the V sin I should probe basically like the tau of 2/3 surface or something like that. And so the seismology should be probing interior to that, but not very much. So it's you got the order right, exactly. Yeah. So in this zoom in plot, I have tried to make a guess for a star of that type, what radius that envelope point is probing versus kind of the V Sinai probing one. They are not very far separated, and there are very large, kind of, this region is slightly included error bars that I have not bothered to put on the plot.
The red one is B Sinai and green point is B. Okay. Right,
Yeah.
okay. Thank you very much.
Yeah. Other clarifying questions? Cool. Okay, so that takes you up the red giant branch. So you can make a model then of kind of the average rotation of red giants of various masses. So that's the x-axis here, and various evolutions or evolutionary states or log Gs as they're kind of going up the red giant branch. And so for a star like the sun, a 1 solar mass star, it's got a rotation velocity of about 2 kilometers per second now. So when it gets 10 times bigger, it's going to have a very, very small rotation. You don't really expect it to be detectable. But for a more massive star, even something like 2 or 3 solar masses that's rotating at like 300 kilometers per second on the main sequence, as it turns into a red giant, it will slow down substantially, but that slowed down substantially could still be something like 5, 10, 20 kilometers per second, which you should be able to measure in a reasonable spectrum. And you can do the same kind of calculation in rotation period. And then, of course, you can go out into the data set and say, where do I measure rotation velocities? Where do I detect spot periods for giants? And you'll notice that the pattern of detections looks nothing like the background pattern that my models originally predicted. So one thing you notice is there's this sort of excess of detections at a particular surface gravity that happens to be the surface gravity of the red clump, so the core helium burning phase in this regime. And so these are almost certainly stars that have interacted with something on their way up to the tip of the giant branch. They were too large there to be really detectable in rotation, but when they contracted back down to core helium burning, they retained that angular momentum long enough for you to see this excess of rotation. And this excess is sort of where I'm getting that sort of at least 10% of stars must have interacted with something on the red giant branch, because otherwise angular momentum conservation would not allow this. The other thing you will notice is that the massive stars here, I predicted to be relatively rapidly rotating, and then we did not detect that rapid rotation. We think that part of that is the fact that when I made these predictions, I was using those old simplified angular momentum loss models. Oh, right. Yeah, I was using those old slow angular momentum loss models where I had this kind of simple wind law that just kind of scaled with rotation. Stars would slow down over time, give you a distribution of rotation periods, something like 5, 10, 15, 20 kilometers per second. But if you use some of these more sophisticated angular momentum loss laws that take into account things like the luminosity being brighter, the radius being bigger, the convective overturn timescale being different, right? They predict a different rate of angular momentum loss for these very large, more massive stars that gives you something more like the distribution of rotation velocities of the surface that you see. And so these stars are really spinning more like 3 or 5 kilometers per second in the core helium burning phase, not 10 or 20. You can also ask what the core rotation looks like in this core helium burning phase. This is a region where the modes from the core couple to the envelope very nicely. You can measure rotation rates for the cores of these stars as they evolve in core helium burning. So that's from left to right on this plot. Here I'm still focusing on those kind of 2 to 3 solar mass stars. And what you see is there is a clear trend in the core rotation periods with surface gravity. Now, the cores of these stars are not really changing in moment of inertia over the course of this. They're getting a little bit more massive, but the radius is changing a little bit. And so basically the moment of inertia is fixed. So the fact that these are slowing down means that they must somehow know that the envelopes are expanding in this regime, which is kind of model independent evidence that there must be significant angular momentum transport between the cores and surfaces in the core helium burning phase. Now you can also predict what the distribution of surface rotation rate should look like for these stars using these more sophisticated angular momentum loss laws that we think are better. In general, you get something with about this same trend, but maybe a factor of 2 slower. So the amount of radial differential rotation in the core helium burning phase is only a factor of a few, which is very different from those very large differences we saw in the red giant branch. Now you can also look in this sample and see if there are trends with stellar mass. I don't really see any. If there are trends with stellar metallicity, I mean, we don't have a very large metallicity range, but I also don't really see any. The wiggles here are just me trying to model the exact sample of stars that I actually observed. You can look at the contrast between the surface and the cores of these stars. In general, like I said, it's about a factor of 2. The pink band here is what would happen if you had a little bit of radial differential rotation in the convective envelope of these stars. It's a giant convective envelope. It's evolving relatively rapidly. Unlike our sun, it's not clear that the inside of the convective envelope should rotate at exactly the same speed as the outside. So maybe allow a little bit of radial differential rotation with some profile that scales as r to the -1 or something like that. That would give you the sort of contrast rates of this pink band. So you do not necessarily, you could have all of the radial differential rotation of these core helium burning stars be in the surface convection zone. That is not true on the red giant branch or the subgiant branch. But in this regime, it is possible that that is true. It doesn't mean that there's not also radial differential rotation in the radiative zone. We can't probe that. But it doesn't necessarily have to have that in the same way that it does on the subgiant branch and red giant branch. So in the core helium burning phase, we see surface rotation rates that are somewhat mass dependent, core rotation rates that have very minimal mass dependence. We see a minimal metallicity dependence, except for maybe the number of binaries. We see much less radial differential rotation than we saw on the first descent red giant branch. So clearly angular momentum transport has happened in between. And we know that binaries can spin up the surfaces of these stars. So hopefully I've convinced you over the course of this talk that we have empirical data on the evolution of stellar rotation from the pre-main sequence through the main sequence through the red giant branch. And that binaries are not a negligible part of this process, that more than 10% of stars are interacting with something over the course of their lifetime, and that we can start to identify these systems, identify them pre-interaction, identify them during the interaction, identify them post-interaction. And that there's quite a bit of physics that's going into this tracing of the angular momentum and the rotation rates of these stars. You've got angular momentum loss, but you're turning it on the pre-main sequence. You're kind of stopping it on the main sequence. You're turning it back on the red giant branch, and it kind of continues. Similarly, you've got internal angular momentum transport that varies over the course of the star's lifetime. You see that kind of decoupling between decoupling and recoupling of stars on the pre-main sequence between their cores and the envelopes. They're pretty strongly coupled on the main sequence, seem to decouple significantly on the red giant branch, recouple in the core helium burning phase, and then probably again decouple on the AGB. And that you can trace these tidal synchronization processes. So I think I'm going to stop there and ask if there are any questions. Yeah.
I have 2 questions, and one is that I think you have shown that core rotation speed is not dependent on the metallicity or stellar mass or something. And does that depend on magnetic field strength? Because magnetic field strength, if there's magnetic field, I think that could work to transport angular momentum to the envelope, which slows down the core.
Yeah.
Is it possible to measure the magnetic field of the star?
Yeah, so this is a great question. It is something we would love to do, and the universe conspires against us. So there have been arguments that having a strong magnetic field in your interior should impact the modes. People have shown this in kind of, as you crank up the magnetic fields, the modes frequencies change a little bit, and then eventually that sort of coupling between the core and the surface goes away for those modes that are strongly magnetically influenced. You have this kind of magnetic greenhouse effect. And so you stop seeing those dipole modes that we were using to probe the rotation. So the stars where we think we have the strongest interior magnetic field, we cannot measure the core rotation rates of, which is extremely annoying. We have looked for correlations between things like magnetic activity at the surface and the core rotation rate. We haven't seen much, but that's not exactly the regime that you would really care about for these stars. And so inconclusively no, but I would love to come up with a way to probe that because it should be very interesting.
And the second question is there a difference between single rotating stars and some stars that are spun up the binary mass transfer?
Yes. What do you mean by differences?
Like the, I don't know, the core rotation speed or
Yep.
chemical abundances inside stars.
Yeah. So at least in low mass stars, for the few cases like the one I showed where we think there's some interaction happening that's spinning up the surface of the star, we have not seen a deviation from kind of the average or range of averages of the core rotation from those stars.
Okay.
Now that could mean that the stars kind of tidally synchronizing into out. That's when you start really dumping material on, then you should start really seeing changes in the whole structure, especially if you kind of let it stabilize over time. In low mass stars, I don't think we have a ton of great constraints. In more massive stars, people are starting to look at that, but you don't get the same interior profile in exactly the same way.
Okay, thank you very much.
Was there ever a situation in any of the various core envelope couplings or differential rotation that you presented where there was angular momentum flux into the core through the core envelope boundary? That's related to this last question, but not just for special stars that have mass transport at their surface.
So for kind of standard low mass star evolution, at least the post-mean sequence where I've looked at more carefully, in general, the core is contracting and the envelope is expanding. And so depending on exactly where you draw the boundary, you don't see, the flux should be going outwards.
Right. I'm wondering if that's observationally verifiable or
Ooh,
not.
I have not seen a clever way to verify that. There are definitely the few special cases where it should be going the other way. I haven't seen it yet, but I think we will eventually. But the going out direction, I haven't seen a clever way of measuring. Yeah.
Have you considered or looked at relative rates of main sequence stars and binaries and the red clump stars? And the reason that I ask about this is because when I think about stars going up the red giant branch, I mostly think about them in context of going into Roche overflow, and I would expect that what you're actually seeing on the red clump is stars that have tidally spun up but didn't quite Roche overflow. And so I'm curious about relative rates like going in versus what comes back from tides versus what actually goes into Roche overflow.
Yeah, I think that detailed modeling is ripe. I've seen people do kind of a simpler look at it in terms of like carbon to nitrogen and other kind of mixing diagnostics. And my impression is the numbers sort of work out, but like the detailed, like what regime of orbital periods must it have interacted with, I don't think I've seen yet. And part of that is it's hard to think about how you would do the completeness corrections because I give you a list of things I measured, but sometimes I forget to tell you what the set of things I looked at was. But it's starting to become more possible, and I think it would be very, very interesting to do.
Awesome, thanks.
Yeah. Other questions?
Is it reasonable to assume that some of these mysterious things that may have interacted with the surfaces of these stars are planets?
Yeah, I think so. I mean, part of it is it must happen, right? Hot Jupiters exist, and those orbits are inside the star by the tip of the giant branch. So there must be an interaction happening there. For ours, the one I was talking about with the 3-point rotation profile, we sort of did a check for, is there an obvious stellar companion there? We don't see anything, so we can put some sort of limits on kind of the massive thing you could have be in there and not see it. They're, not super interesting, M dwarf, low mass, brown dwarf, planet-y thing. But we are starting to put, as people are kind of coming from the planet side, trying to find those close in stellar planetary companions to subgiant and red giant stars. Those people are starting to look for evolution in the orbital period, which would tell you that tidal interaction is happening from the other side. And then on our end, we're picking out these stars, and we've picked them out. There's this sample of stars that are rapidly rotating, but we don't see a radial velocity variation above some level. So some of those probably are planetary, but we haven't done the detailed radial velocity characterization to put the limits on exactly what. But I think that is happening from all sides, and so that interaction is going to be very interesting. And people are really excited about how it affects things like the chemistries of the stars. Can you diagnose it with lithium? Things like that. Question?
Yeah, in a similar vein, so if you have like a measurement of a faster rotation at the surface and a slightly slower rotation just beneath the surface, can you use that difference to place constraints on, say, the orbital period of the companion itself, or that kind of thing? Like, is that physically related?
I have been working under the assumption that the rotation of the surface of the star is related to the orbital or the pseudo-synchronization period of the companion. That is an assumption I have made that somebody who does detailed dynamical modeling should probably check. And similarly, somebody who does detailed interior, how do you drive the tidal waves that actually do the synchronization? That's sort of how it should work, but like exactly the details of that, I don't think have been probed. So I think there is absolutely the possibility of kind of probing that sort of physics, but you kind of want either a really good system that you study very well, or an ensemble of systems that have been pegged as exactly this. And I'm not sure we've quite built that ensemble yet.
That makes sense. Thank you.
Yeah. Other questions? Or Zoom questions? Or Zoom questions?
On Zoom, I think Matteo was responding to the question.
Beautiful.
He says that engulfing hot Jupiters won't spin stars to detectable rotational velocities, but things about 10 Jupiter masses and above can begin to do the trick.
So there are models that argue that a 1 Jupiter mass star in a particular range of log G's at a particular direction limit should be detectable as an increase in the rotation rate of, few kilometers per second. But now that you EPRV people are doing extremely precise spectroscopy, oh, thank you, computer, that's what I wanted. Doing these very high resolution spectra, right? Like a rotation velocity of 3, 5, 8 kilometers per second is achievable. And so you have to get the right system, but you might be able to detect that.
And then also on Zoom, Adrian says, and we have RV detected short period binaries from apogee with low mass companions that might give a sense of overall rate. So I guess we should chat because the selection function for that is relatively simple.
Yeah, that would be a very interesting sample to start looking for this stuff, because you know exactly what you can detect, how you detected it, and kind of put together the ensemble and the system properties would be really, really cool.